Okay, folks, this is our test review / study guide for our first unit test. So we're going to start with transversal, a set of parallel lines and transversal. Small typo here, 55 should be right here and G should be right here. So the idea here is we are figuring out all of the angle measurements. Okay, we can talk about the relationships we have right here. But the information that we start with is the fact that we know, if I can get a highlighter here, we know that this angle right here is 55 degrees. And so if we know that, then we can kind of figure out all of the other angles right here, okay? And so we talk about this in terms of congruence, meaning the same angle measurement, and supplementary, the angles being supplementary, which means that they add up to 180, right? So I've got this one right here. This is an acute angle, so less than 90. All of the acute angles are going to be that same measurement, right? We can talk about it in terms of angle relationships. These would be vertical angles, and if I go here to here, these would be alternate interior angles right here. And if I go back to the first one, and then I look at this one right here, these would be alternate exterior angles, and the characteristics of those relationships are that the angles are congruent, okay? And then the other angles that we're missing are the obtuse angles, right? The idea here is that these two angles will add up to 180. You can think about it as being half a circle right here, and half a circle is 180. 360 divided by 2 is 180. So how you figure out these missing angles right here is you subtract that number from 180, and if we do that, let's use our handy dandy calculator right here. We can get that glare off of there. 180 minus 55 should give us 125. So that's 125 right here. Okay, those two being supplementary, and then I can use the vertical angle relationship right here. I can use that alternate interior here, and then I can do that alternate exterior here, or I can do corresponding angles here, like so. Yeah, and that's kind of how we figure those out. Okay, now we'll take a look at number 2. This is when we get into transformations here. We want to describe 3 different ways that a figure can be transformed to make a congruent copy of itself. So we're looking here for rigid transformations. We've talked about 4 different transformations: translation, reflection, rotation, and dilation. The only one that does not make a congruent copy is dilation. So we take that one away, and we talk about translation. That's when we just move a figure. Reflection is when we flip a figure. And then rotation when we turn a figure. Okay? So these all make rigid transformations because the original and the copy itself are congruent to each other, meaning they're the same size and the same shape. Dilation is the one that does not fit, so I'm going to kind of like separate that down here, and we'll say dilation. This is when you change the size of a figure. I'm doing that right there. Change the size of a figure. So, right, these 3 form congruent copies here, and you know this is what we're talking about in this particular problem, right? So these are the congruent ones, and then this one down here, the dilation, they make similar figures, meaning they're the same shape, but they are different sizes, and more specifically, the sides are in proportion to each other. It's the same number you multiply on each side to get to the bigger figure. Yeah. Okay, so this kid Enrique said that the following transformation proves that these 2 triangles are congruent, and is he correct? So Enrique is saying that we take we translate triangle 1 to the right 4 units, and then down 2 units. So basically, we take this one here, and we go right 4 and then down 2. But we can clearly see that if we know our rights and our lefts and our ups and our downs, that if we take figure 1 and do that, it's going to send it off the grid right here. Okay. So is he correct? No, he is not. And the reason is because he's translating figure 2 rather than figure 1, right? We could adjust this to say that if we went left 4 and up 2, then he would be correct. So we could say if Enrique said go left 4 units, and up 2 units, then he would be correct. There you go. Thank you. Okay, this graph shows the rate at which a factory makes Hot Wheels. Based on the graph, Hot Wheels are being made at a rate of blank per minute, right? And so when we take a look here, we've got this graph. We've got number of Hot Wheels made on our y-axis, and then the time in minutes on our x-axis right here. You can see I've got them labeled here and here. You'll also notice that we are skipping some numbers right here. If it makes you feel more comfortable, you can plug in the odd numbers that this is missing. But you don't have to do that necessarily. That should be 1, not 3, my bad. 3, 5, 7, 9. Okay, so based on the graph, Hot Wheels are being made at a rate of blank per minute. The idea here is we want to find a point where the line goes directly through a corner of the grid, right? And as I look at this line, there's a point right here we could do. There's a point right here that we could do. Okay, so we've got up 3 and over 4, and then from here we've got up 3 again to get to 6 and over 4. You could also think about it as up 6 and over 8, right? Either one is going to work, because when you take that 6 divided by 8 and that 3 divided by 4, you're going to get the same number, right? So up 3 and right 4, if I do that division, I get a fraction, or I start with that fraction, 3 divided by 3. If I could type 3 divided by 4, it gives us 0.75. And then 6 divided by 8 will also give us 0.75. So it's going to be the same either way. So they're being made at a rate of 0.75 per minute, or 3/4. I guess I should be writing that right here. So 0.75 or 3/4. Explain the steps you use to determine your answer. If we think about it in terms of what we learned in 7th grade with Miss Sugarman, this would be the constant of proportionality, because this is a proportional relationship. It starts at 0, 0, and then goes up at a constant rate, or the unit rate, right? So it's basically saying that 0.75 Hot Wheels are being made in 1 minute. Okay, so you could say explain the steps used to get your answer. I went up from the origin to get to 3, and then over to get to 4, and that's your constant proportionality. So you could say, I don't know, I found the, let's say unit rate. I like that better, because I'm going to use unit rate in class more than I'm going to use constant proportionality, by going up from the origin and then right. Origin and then right to intersect the graph. And so starting here at the origin, I went up 3 and then right 4, and that's where it intersected. Let's actually say line rather than graph. Model the relationship between the number of minutes x and the number of Hot Wheels made y algebraically excuse me, with an equation. Well, all proportional relationships are going to be in the form of y equals mx. I think in 7th grade it's represented as y equals kx, because I think k is the constant proportionality, I believe. But anyway, this m value, that's your unit rate, and that's our unit rate right there, so that's 3/4. So you could say y equals 3/4 x, and that'll do it for you. Okay. For number 5, all we're doing is kind of like labeling this graph, right? We have quadrant 1 right here. Your x and y values are both positive here, and as we move around in a counterclockwise fashion, we go from quadrant 1 to quadrant 2, where our x values are negative and our y values are positive. Oh, and this one, let me make sure that these are labeled. They're both positive in quadrant 1. As we move on to quadrant 3, your x values are negative and your y values are negative. And then as we move into quadrant 4, your x values are positive and your y values are negative. This is our x-axis, the horizontal axis, and then that vertical axis is your y-axis, right? And yeah, so that's how we would label our set of axes right there. Little typo, I was moving fast this morning, and I decided to relabel after I had finished this problem, so I didn't didn't change the instructions. But anyway, I've got DEF and I've got JKL right here. So side JL here is 8 inches longer than side DF here. 4 plus 8 gets you to 12, okay? So can we add 8 inches to FE, which is this one right here, to get to LK, and why or why not, okay? So this is a dilation, right? We talked about this briefly earlier. This is one of our non-rigid transformations. The idea here with a dilation is that the shape will be the same, but the size will be different, and more accurately, it means that the sides will be in proportion to each other, right? So what we've done in class is we've used our scale factor to multiply rather than add, right? We haven't added the scale factor to anything, right? So if I kind of like figure out what number I can multiply 4 by to get to 12, then that's going to guide me on my other sides right here, right? If I take 4 and rather than adding 8, I multiply it by 3, 4 times 3 gets me to 12, 3 times 3 would get me to 9, right? And then reversing backwards rather than multiply, let's divide. 15 divided by 3 would get us to 5 inches, right? So if I added 3 here, sorry, if I took 3 and I added 8, that would give me to 11 here, and then 5 plus 8 would give me to 13 here. So these values would definitely be off if that were the case, if I were adding rather than multiplying by the scale factor, okay? So can you add 8 inches to FE to get LK? Why or why not? No, you cannot. And you could say something like you multiply your side lengths. Let's be real specific and say your original's side lengths by the scale factor rather than adding by the scale factor rather than adding to find your new image. Explain the steps needed to determine the length of side LK. So LK is right here. We would take our scale factor of 3. That's 4 times 3 is 12, right? So, and we would multiply it by FE. So 3 times 3 would get to 9. So what are the steps? You would take side FE, which is 3 inches, and multiply by the scale factor of 3 to get LK, which is 9 inches. So what is the side length of DE? We've already figured this out. 5 inches, side length of LK is 9 inches right there, okay? Which figures are rigid transformations of each other? Circle the congruent figures. Okay, again, congruent figures are what happens after rigid transformation. So translation, reflection and rotation. And this goes back to, I think, number 2, when we went through the rigid transformations, translations, reflections, and rotations, and not dilating, not changing the size or shape of the figure. So the only ones that are congruent are A and B, not C, and not D. There you go. Again, congruent, right, means same size, same shape. When we talk about the same shape, we also talk about the same angle measurements. Okay. Triangle XYZ will be rotated in a 90-degree counterclockwise direction to form triangle X prime, Y prime, Z prime. Determine the location of Z prime. So if we talk about a 90-degree counterclockwise, whole thing on here. So 90 degrees counterclockwise is going to go down here, okay, into quadrant 3. Right. So we know, based on our graph earlier, that we're expecting our points to be negative once they transfer into this area right here. So what I'm going to do is I'm going to record the coordinates of x, y, and z. So x is negative 2, 1. Okay, and we know that these are negative and these are positive, right? So that matches right there. Y is negative 4, 4. The x value goes first, the y value goes second, and then z is negative 1, 6. Now, if I say x and y, and you're like, but the x and y are here too, these are points, right? Just realize that these could be any letters. This could be A, B, C, D, E, F, whatever, right? I just chose x, y, z because why not? And so the idea here, when you're transferring or rotating down here, if you think about it as like pointing down here, as it rotates around the center, it's gonna like, what's the best way to do this? If it's pointing down here and it rotates around the center, it's gonna like go like that and be pointing to the right, right? If you can imagine that this is that triangle right there, okay? And so what we do here is we take each of our points and we flip-flop the order of the numbers, and then we match them to the destination we're going to, right? So I take x, and I go x prime, I flip them around, and I make them both negative, because that's the destination where I'm going to go to. So negative 1, negative 2. Y prime is going to give us a negative 4 as I flip them and make them both negative, and then z prime is going to give us a negative 6, negative 1 right there. So as we do that, right, we can see that negative 1, negative 2 is right here for x prime, negative 4 for y prime, and z prime is negative 6, negative 1 right here. So okay, and if I look at z, it's negative 6, negative 1, and that's what I'm looking for, is the location of z prime. Okay, answer the questions below. Is this a reflection? Why or why not? If yes, what is the rule? Is it a rotation? Why or why not? If yes, what is the rule? Is it a translation? Why or why not? If yes, what is the rule? Is this a reflection? Well, if it was a reflection, it would either be reflecting over the y-axis or the x-axis. And if it was like, if you can imagine it as like pointing left for this, actually, since this is the original, let's go here. I know that this is the original because this one has the little prime notation on it to indicate that this is the new one. So actually, let's label this as the pre-image first. And this is the image or new one second. Original one, new one. If I reflected this across the y-axis here, if you can imagine it pointing left, it would flip and it would be pointing right, and that is not what it looks like. And if you can imagine it as pointing up, and I flipped it over the x-axis up here, it would be pointing down. So, is this a reflection? Why or why not? No, it is not. Okay, is this a rotation? Why or why not? If so, what's the rule? Well, if it rotated, it would be, again, pointing in a different direction, right? So if I rotated it up, it would be basically pointing up rather than left, right? But they're both pointing in the same direction, so it can't be a rotation, okay? So no, it is not. And is this a translation? Why or why not? If yes, what is the rule? Yeah, so, I mean, yes it is, because it looks like it's just been moved. They're pointing in the same direction. So yes it is. Yes it is. Because, B/C, you know, it's how I abbreviate because they are pointing in the same direction. And are just in different places. Yeah, rather than places, let's say locations. Okay, now the rule is basically we go from point to point. So if I take a look at point U and I compare it to point U prime, right? I would have gone 1, 2, 3, 4, 5 right, and then up 1, 2, 3, 4. So it would have translated 5 right and 4 up. You could also say this as x plus 5, because that's on the x-axis, that left and right, or y plus 4. Two different ways to write that. These are both valid answers. Okay. Okay. 10. are these triangles congruent or similar? Explain. So we're looking at these two right here. I would say that they're congruent, because again, congruent means same size and same shape. So I'd say congruent, and then, yeah, they're the same size, and then the same shape or angle measures. You could also talk about this in terms of what transformation got you from one to the other. So again, this is the original, this is the new one. This has the little prime notation, might be kind of hard to see, but it's got the little apostrophes here, right? This would be a reflection across the x-axis, and right, D is pointing up here, and it ends up pointing down right there, right? So this would be, if we wrote the rule for this, this would be a reflection over the x-axis. Okay, so these are congruent. Now we take a look at this one. Clearly we have two different sizes right here, so right away we know it's not congruent, right? And if for similar, right, we would want to compare the same shape, and if we can determine if it's the same shape, I mean, it just looks like it, right? You can kind of just tell that it is, right? So we would say that they're similar. So same shape or same angle measures, right? Okay, it's kind of like the same thing, right? Having the same angle measures is what forces them to be the same shape. And it would be a different size, right? Or technically, it would be the sizes are in proportion. Okay, and like we could like work this out by figuring out that A, let's see, is at 0, 2. So A is 0, 2. B is, let's see, 2, negative 1. And then C is, looks like, negative 2, negative 2. All right, and then we compare, let's say if we do A, that's 0, 4. A prime is 0, 4. B prime is 4, negative 2. And then C prime is negative 4, negative 4. Let's shift that up so we can see it all. And so what we're seeing here, when we talk about the sizes being in proportion, we're talking about the scale factor, right? We're multiplying each of these points by the same scale factor, right? And so I know if I multiply 2 times 2, I get to 4, right? And 0 times 2 is 0. And then 2 times 2 is 4. Negative 1 times 2 is negative 2. 0 times 2 is, oh, sorry, negative 2 times 2 is negative 4, and then negative 2 times 2 is negative 4 here, right? So I'm multiplying every point by the same numbers. That's our scale factors. That's what it means when it says that they're in proportion to each other. And yeah, there you go. So congruent, same shape, same size, and then similar, same shape, different size. It's kind of like the most simple explanation. If you want to be more precise for similar, you would say the sizes are in proportion, and when you're talking about the same shape, you'd say they have the same angle measurements. So there you go. Okay, so equation. This is a proportional equation, so we know it's going to go through 0, 0, so starting here, and then we're going to go up 2 and 3 to the right. The number on top controls whether you go up or down. The number on the bottom controls whether you go right. Okay. If this were negative, we would go down, but since it's positive, we'll go up 2 and then right by 3. Okay? Now I can get another point by reversing it, so rather than up 2 and right 3, I can go down 2 and left 3, just like so, and then I will graph that right there. Okay. Now what we're going to do is we're going to translate the equation down by 4 units. So I'm just going to, like I said, I didn't need 2 graphs for this, because then it's just like doing extra work here. All right, so this is the original. You know, you can put this, you can put it on one graph. You don't need to duplicate that. It doesn't really matter. And then we're going to go translate the equation down by 4 units. So down by 4. We're just going to take each point and move it down 4. So 1, 2, 3, 4. 1, 2, 3, 4. And then this one would go off the grid, so we're not going to worry about that, because technically all you need to draw a line is 2 points, and we have 2 points. Okay. So all we've done is we've taken this, we've moved it down 4 units. We have 2 parallel lines here. Okay. Yeah, so to kind of get into it right here, if we adjusted our equation, this would be y equals 2/3 x minus 4. Rather than starting at 0, right? Rather than starting at 0 for this proportional relationship, we are starting at -4 and then going up 2 and right 3 for this non-proportional relationship. Okay. All right. Last one. This is the big boy right here. So we're going to reflect this triangle over the x-axis to form triangle x prime, y prime, z prime. Then we're going to dilate it by a scale factor of 2 using y prime as the center of dilation to form triangle x double prime, y double prime, z double prime. Okay, so that's what's different about this dilation is we're using a different point rather than the center. Okay, so let's look at first. Okay, so we're going to reflect over the, what did I say, x-axis. So x-axis is again the horizontal axis here. Okay. So how you do a reflection is you figure out how far each point is from that line, and then you go directly on the other side that same distance. So x is 1, so x prime is 1. Z is 3, so z prime is 1, 2, 3 down. And y is 2, so y prime is 2 down right there. Okay. So now we have our reflection. We have flipped our shape. Let's make sure we're using a straight edge to be precise here. Again, could be the edge of a book, could be the edge of a note card, really anything. Because you want to be precise here. Okay, so we've got our reflection right there. Okay. So let's cross that out. So we've done our reflection. Now we're going to dilate by a scale factor of 2. Now, the idea here is that we're going to make a set of temporary axes at y prime, and we're going to kind of forget about the original set of axes, that x and y, until the end when we kind of go back to it, right? So what's going to be the best way to rep this? Well, I guess I'll just do the brown. Okay. So what I'm going to do is I'm going to draw a small set of temporary axes here. Okay? Now, since y prime is the center, right, y double prime is not going to move. Y double prime, as we make it, is going to stay right there, and then these 2 points are going to, like, move this way, okay? And so we can basically just compare the distance from y prime to x prime. It's 1, 2, 3, 4, 1. Sorry, -4, because it's left 1, right? And so then the new point after we dilate it by a scale factor of 2 is going to be a -8, 2. So we would go left 8, 1, 2, 3, 4. What's it? 1, 2, 3, 4, 5, 6, 7, 8, and then up 2 right there. That becomes x double prime. Okay? And then we do the same thing. We compare y prime to z prime. It is 1, 2, 3, 4, 5 left and 1 down. So basically, temporarily, -5, -1, and we double that to get -10, -2. And so basically I'm just going to double the distance, right? I'm going to go over 10. So 6, 7, 8, 9, 10, and then down 1, 2. And that should get me where I need to be. Let's double check before I commit. Okay. Now I'm going to use a straight edge. Okay, just like so. Okay, so now we have our reflection, and then we have our dilation by a scale factor of 2 from this point. And now we forget about these axes, okay? And then I'm actually going to skip this part of it, okay? And then I'm going to do this, and then we'll go back to it, okay? So it's asking for the coordinates of the new ones, right? So x double prime from the original origin, not the temporary one, because we forget about this. I should have written that in pencil and erased it. That would have been smart. What are you going to do? So this is -2, 0. The left, since it's going left on the x-axis, it's negative. And then y prime is, again, from here, right 6 and down 2. So 6, -2 for y double prime, the same point as y prime. And then, let's see, left 4, down 4 for Z double prime, okay? Yeah, that's kind of how you figure that out. So is triangle x double prime, y double prime, z double prime congruent to triangle x, y, z? So we're comparing the original one here to this big one here. Now, sorry, the original here compared to the big one here. Okay, now hopefully we've talked about this enough that we remember that to be congruent, you need to be the same shape and same size, right? But since we're not the same size, we're definitely not congruent, right? Similar, again, sides are in proportion. We use that scale factor to make sure the sides are in proportion to each other, okay? And so please explain. So we'd say they are similar because they are the same shape. That's an awkward way to write this, slash have the same angle measures, and the sides are in proportion to each other. We're multiplying by that same scale factor of 2 are in proportion to each other. So that's what makes them proportionate. Well, there you go. Hope that was fun.